Our second feature for today, we have all Zamir.
So thank you. I'm very happy to be back. I'm also happy that I had an hour to defrost before the talk. Okay, I'm going to talk about joint work with Vinod, about how we can use cryptography to improve the efficiency of algorithms. Unlike Amir's talk, I am intending to say nothing about any fancy tools. I'm trying to use only the simplest tools possible for everything. Nothing fancy will be here, and also I will not assume knowledge about anything. Good. So let's just say a few words about cryptography. Obviously, at this point, we have many years where people worked extensively on cryptography. We have a very large body of work, very impressive arsenal of tools. Most of them are used for cryptographic purposes. This is a very uninspiring tautology, but what I mean by that is that we usually use it for things like privacy and security and trust and so on. But we do have, from the very beginning, a few applications of either cryptography or cryptography-inspired notions for some other things outside of these cryptographic purposes. For example, things like reducing randomness or de-randomizing things, or reducing interactions, say Fiat-Shamir and things like that. So we have seen a few examples of using these tools out of cryptography, but what we are going to ask is, can we use the same cryptographic tools or notions for maybe the most basic algorithmic task, which is improving the running times of problems? And the only notion from cryptography I would need is the classic notion of computational indistinguishability. So what is that? The formal definition doesn't matter that much. What I need is the essence of it, which is that cryptographic or computational indistinguishability means that I have two distributions such that any polynomial time algorithm cannot distinguish between them. Meaning that for every polynomial time algorithm, if I would allow it to take samples from the first distribution, or alternatively, I would allow it to take samples from the second distribution, but I will not tell it which, it will not be able to say with non-negligible probability which of the two distributions it's on, usually assuming some cryptographic hardness conjecture. Yes, so the entire notion is I can't distinguish between two distributions. I will not need anything more than that. And this comes up a lot in cryptography. So in some obvious things that should come to mind when I'm saying this, things like a pseudo-random number generator or program obfuscation or so on. But even when you are trying to define encryption, then indistinguishability is the easiest, nicest way to define it. Saying something like for any two inputs, the encryption, if I don't have the key, is indistinguishable from each other. So I can't tell anything about which input I saw, and so on. But this encryption example is good because this also shows us some asterisk that we usually have there, is that usually when we use indistinguishability, the indistinguishability is maintained only as long as we don't have access to some secret key. Right, so for example, back in the example of encryption, if I do have the key, I can decrypt. So obviously this doesn't look random anymore. This does distinguish different inputs at this point, but without the key, it is indistinguishable from each other. Or say with a PRG, maybe also if I have a secret key, I'm now able to generate the next numbers myself. So things stop looking random when I have this secret key. And the new notion we want to introduce is something we will call an efficiency trapdoor, which will follow along the same lines, but now there will be something else that I can do when I have the key. So now what I would want is to have some distribution of functions such that if I don't have a secret key, then this distribution of functions is indistinguishable from the actual distribution, say uniform distribution or some distribution we care of. But if I do have the key, for some reason, I can apply the function that I sampled very quickly. So now the thing that the key gives me is the ability to apply a function very quickly.
Like computer.
Yes, to compute it on any input. This is a circuit, essentially. So maybe to be more concrete, here is like one more concrete instantiation of this that we introduced called Trapdoor Matrix families. So this is going to be a distribution of pairs of a matrix and a circuit, such that the marginal distribution only on the matrix, if I show you just the matrix that I sampled out of this distribution, this is indistinguishable from a random matrix.
Without assumption.
With assumptions,
With
it's computationally indistinguishable under some assumptions from a random matrix. But that circuit exactly computes the matrix vector product with the matrix that came with it out of the distribution, and it is a near linear size circuit, or a circuit that is very easy to compute.
So this should be in the first bullet, really. It's the distribution on pairs where the circuit is nearly linear.
Yes, yes. But I mean, I wanted to give it some flexibility because I will show you first the construction, which it is not nearly linear, but just have a matrix and the circuit that computes it.
So M is M by N and C is like in Euler.
Yes. So I'm leaving several gaps because I will fill them with some examples very soon. Okay, good. So to try to fill the gaps, so I also need to say what is a random matrix. So we show constructions for this that are uniform under over finite fields, but also for distributions of matrices over the reals. So we can do this for currently for any distribution that is rotation invariant. So say matrices of random Gaussians, but also, I don't know, orthogonal ensembles and so on. So a concrete example, we show that for any finite field, we can construct such a trapdoor matrix family distribution for the uniform distribution over the finite field for say square n by n matrices, where the running time of the circuit is near linear. And we can do this from several conjectures. So we can do this, say, from the LPM conjecture or the Michaelis conjecture, and probably from several others as well. So you do need to assume some conjecture, but in the end, I will get to why it doesn't really matter which. You can do it from many, many different conjectures. Good, and one extra thing to mention is that we do need to have some computational assumption. We do need to have a conjecture. Why? Because the mere existence of such a small circuit, this is surprising. This is something that entropy-wise shouldn't happen. So without any computational assumptions, just checking whether or not there is a small circuit will be a distinguisher. Good, and I will also say, but for most of the talk we will not need it, that we can do it in such a way that we can have small circuit not only for a matrix vector multiplication, but also to many other operations using this matrix. So for example, getting matrix multiplication is easy, right? Because if matrix vector is linear, then of course matrix is linear as well. But we can also multiply with the transpose or with the inverse and so on, and all of this in linear time, if we construct it correctly. And now I want to explain the general recipe of how can we use this creature to turn algorithms into faster algorithms. So the general recipe we have in mind is as follows. Say we have an algorithm that at some point samples a random matrix for whatever reason. Soon we will see examples of this actually happening. And then at later points, it uses this random matrix. Say it looks at specific vectors, multiplies them by this matrix, and does something with the output. Then any such algorithm, I can make it faster. Why? Because I can first take this random matrix that is sampled here and replace it with sampling a matrix for my trapdoor distribution. Right? And so far, I couldn't have changed anything. Why couldn't I have changed anything? Because this is a polynomial time algorithm. So if either the correctness or the runtime or anything would have changed, this would have been a distinguisher. So there cannot be any noticeable change or any non-negligible probability change to what happens in the algorithm by changing the distribution of actual random matrices to this pseudo-random distribution of matrices. But now, after I did that, every time that I multiply by A, I can replace it with my circuit, that computes exactly the matrix vector multiplication. So this also didn't change anything in terms of correctness and so on.
How much time do you allow the distinguisher?
Good. So if we are using a cryptographic conjecture, I usually assume that any polytime algorithm will not be a distinguisher, but I will very soon get to exactly that.
Allow yourself much.
Yes. Yes. Good. And this change also didn't change anything, right? Because this is now functionally exactly the same. just replace the matrix multiplication with something that computes exactly the same function. So this also didn't change the correctness at all, or what is computed at all as a function, but now the running time is lower. Every time that the matrix multiplication previously took me quadratic time, now it takes me only linear time or near linear. So I have something that completely preserved correctness, but the efficiency is improved now because of what happened to these lines. And as Avi said, we are actually relying on the cryptographic assumptions in a much, much weaker way than we usually do in cryptography. Because usually in cryptography, we are saying something like, there is no polytime algorithm that breaks LPN when it tries to break LPN. It can use any polynomial time, and its intention is to break LPN. Now we'll say something like, this innocent quadratic time or cubic time algorithm doesn't break LPN by chance, which is a weaker way to use these assumptions. Good. So now I want to give you a couple of examples to try and convince you that this structure actually happens, that we do have algorithms that look like this. Something can gain from this. The most obvious example is everything related to dimension reductions. So the classic Johnson-Lindenstrauss lemma says that I always can take any set of n points in any possibly large Euclidean dimension and map them into a set of n points in a much lower dimension, such that all pairwise distances will be preserved up to, say, 1 plus minus epsilon.
But here the matrix is narrow anyway, it's nearly narrow.
Good. So I'll say a couple of things about that soon. But yes, what are the, how do I do this, and what is the dimension that I can reduce the set of points to? So for this, all I will need is a random linear transformation. This would be good enough for this to work, for JL to be proven. And the dimension I would need would be something like log the number of points over how much error I'm willing to have squared. And as I said, this might be like in many, many applications, this is small anyway. In some applications, it is not small. If I need okay, first of all, this is very useful in geometric algorithms of various sorts and so on. Yes, if epsilon is relatively large, then this is quite small and this matrix is quite narrow anyway. There came many applications in which you needed this to be slightly larger, and this is why people worked on something called sparse JL transforms. So there is a way to make it faster. There are ways to have this type of matrices that are even faster than doing this matrix multiplication. So maybe this is solved, maybe we don't have to do anything. But there is some problem. The problem is that besides this original JL lemma, there are nowadays many JL type lemmas. What do I mean by that? So there are many other settings that are similar. I have something in higher dimension. I want to reduce the dimension and preserve some things that are slightly more complicated. So one example of these things could be like, I don't have a bound on the number of points I have, but I know something about, say, they are coming from a manifold, or they are coming from some low intrinsic dimension, some space of low doubling dimension, and so on. This comes up a lot now in machine learning related applications, because people are saying something like the data is represented using very large vectors, but it has a small intrinsic dimension. So I want to reduce the dimension, but actually the clusters, say, will be preserved. And this comes to the second thing that is changing. In many applications, what I want to preserve is not necessarily just the pairwise distances, but maybe some other measure. Say the clustering, or like the top clusters, or cuts, or MST, and things like that. So we have a lot of those variants of the Johnson-Lindenstrauss lemma. Some of them require a much larger output dimension, say if I'm trying to preserve a subset, like an entire linear subset or something like that. But it turns out that for everything I wrote here and many other variants, a random linear projection works. You take a random matrix and you prove that you get whatever you wanted, whichever properties you wanted preserved. The problem is that the sparse variants no longer work. And when people cared enough, they needed to work very hard for each specific variant to show that you can still have some quick dimension reduction transform specifically for that variant. And what we are saying is that this trapdoor matrix family would work for any of them. because anything that you could have done with a random matrix, now you can do with a matrix that is sparse in the sense that you have fast multiplication. So we have some examples, especially in this ML-related settings, in which we didn't know how to do it before, and now we have a dimension reduction, again, that preserves whatever you want. Good, so this was the first example. Now I'll give you an example that is maybe slightly less obvious, not something that just says, okay, let's take a random matrix and do something with it. It's not super directly. And this is about worst case to average case reductions for linear algebraic tasks. So a classic result of Bloom, Luby, and Rubinfeld is the following. They show that if we have some algorithm that computes the multiplication of random matrices over a finite field. What do I mean by that? I mean that I have an algorithm such that if I take a random pair of matrices in my finite field, then with probability strictly larger than 3/4 over which input pair I chose, my algorithm returns the correct matrix multiplication of them. If I have something like this, then I can construct another algorithm, A prime, that multiplies any pair of matrices over the same finite field in a very similar type. So this is a classical result, and the proof is very simple. So let's just see it. The proof is the following. They are saying, let's draw two random matrices over my finite field and write down A times B. These are my worst case any two specific matrices as this thing. A plus R1 times B plus R2. And then let's remove what we need, minus R1 times B plus R2 minus A plus R1 times R2. And then we add what we removed twice. We add R1 times R2. And what we can observe is that marginally, each of those matrix multiplications is of two uniform matrices. Right? Because whichever matrix I take, if I add a random matrix to it over a finite field, it becomes fully random. So each of these marginally is just a pair of, like a uniform pair of random matrices, meaning that I can take my algorithm that does exactly that, multiplies two random matrices, and query it with each of these pairs. So now, these four queries are very dependent, but each of them marginally is uniform. And then what they are saying is that if the success probability was strictly larger than 3/4, then I can just take a union bound over the failure probability of my algorithm. Right, so despite the dependence, this one will fail with probability strictly less than 1/4, so are the others. So I have some non-negligible probability, some epsilon probability or constant time epsilon probability that all four will return the correct answer. Good. So I fully succeed with probability at least for epsilon, and if epsilon is constant, why is that enough?
Matrix mult checker.
Exactly, because I can verify matrix multiplication very easily. Right, so I will try like 1 over epsilon times. Each times I only need quadratic time to check if I got the correct result or not. So finally I will get the correct one in time that is very similar to the time of this black box. But now we have a problem with this reduction, which is that it is not clear at all that this 3/4 is necessary. It was necessary because of the dependencies, but it's completely not clear that it should be there. Why not half? And why not 1 over 100? Why not just the success probability epsilon? And so on. And people for a long time thought about that. And recently-ish, in the last 3-4 years, with a lot of quite heavy additive combinatorics, additive number theory works, people managed to show that you can actually do the same for any constant epsilon, with a rather poor dependence on epsilon, but you can do the same for every epsilon.
The later works just use error correcting codes, like list of codable codes.
They use, but they still need the dependence on epsilon be doubly exponential.
Yeah,
But yes, no, the latest works are simplifying the previous ones. Yes, but just saying relatively heavy machinery, relatively bad dependence on epsilon, but it comes from the fact that this is, I mean, like you need to be, it already seemed like you need to be very unlucky for these things to be that badly dependent, and what they end up showing is that they aren't, or that you can make it that they aren't. Right, so yeah, as Max is saying, like the earlier works were more of the form of let's show that it doesn't happen. The later works are more of the form of let's make sure it doesn't happen, which is easier. Okay, good. But what I want to say is that using our trapdoor matrices, now assuming some cryptographic conjecture, we can do this trivially. Why can we do this trivially? Because if instead of taking random R1 and R2, I will take trapdoored R1 and R2, then from the point of view of this algorithm that runs in less than cubic time, it is the same. Like it cannot see that I'm not giving it two random matrices. The distribution of inputs it is getting is indistinguishable from two uniform matrices. So at least this call will have the same success probability as before, unless this algorithm is a distinguisher. But these three calls are now very easy. Why are these three calls very easy? Because each of them has a multiplication with one of my trapdoor matrices. And all of those I can do in linear time by myself. So actually I don't need to make any of the other three calls. The other three multiplications I can do at home in quadratic time. Right, so I have only one multiplication now that I need to do, which means that if this one had success probability epsilon, then now the entire thing would have success probability epsilon. So I'm done. I don't need to do anything. Good. Again, unless this happens to be an LPN distinguisher, which would also make me happy. So I'm happy anyway. Actually, yeah, there is some open question here that I will mention at the end of maybe there is a sort of a win-win argument here, because in either case, I do something linear algebraic way too fast. Right, so either I have like the matrix multiplication algorithm that is too fast, or I manage to break LPN faster than matrix multiplication. Which is, okay. Good. Example 2++, also related to things that other people mentioned, also things I think that Avi, you mentioned working about a couple of years ago. What about error correction in matrix multiplication? So previously in this BLR algorithm, we assumed that we have some chance of getting the exact multiplication of the two matrices, the exact product, and otherwise we didn't care. But what if we never get exactly the right product, but we get something that is close to the product, or maybe not even close, but just correlated to the product? In what sense? So this is the weakest sense possible, what I'm going to say right now. Let's say I have an algorithm A, such that on two uniformly drawn matrices A and B, so the input is still uniformly drawn, it gives me something such that the expected Hamming distance between what the algorithm gives me and the actual multiplication is slightly better than just returning a random matrix. So like the Hamming distance is smaller than 1 minus 1 over p minus epsilon times n squared. Without the epsilon, this would have been just what I would get by returning a random matrix every time. So I have an algorithm that on average inputs returns something that is a tiny bit correlated with the result. Can we use that to get in a very similar running time a worst case algorithm for every two input matrices that returns exactly the correct product? And also very recently, this was shown to be possible with non-uniform algorithms, meaning that for every n you need to construct something specific. Afterwards, they also made it uniform unconditionally. But this was the first uniform version of that, again, assuming some cryptographic conjecture in a weak way. But let's see it, because also this would be completely trivial, unlike the previous works. So what could we try to do? So we can notice that if we look at exactly the same reduction as before, then I still have only one call. So on this particular call, that still looks like two random matrices, like input to my average case algorithm. Now I will not get the result with some probability, but I will get the result plus some noise matrix. And what do I know about this noise matrix? So let's denote it by a large epsilon. This is like what I get for my algorithm when I give it two random matrices minus the actual product of these two random matrices. So what I know about this random noise, and notice that this is independent of A and B, of course, right? Because at this point, this is just a random thing. So what I know about this noise matrix, I know that in expectation, the number of zeros in it is slightly too large, slightly larger than I would have got with just a completely random matrix. And because I can do it several times, I can draw R1 and R2 independently several times, then I can get many samples of this thing. And then the question or the hope is, if I have several samples of a distribution of this form, can I use it to get rid of epsilon? Can I sample several times and then just, I don't know, like take the majority or do something like that to get rid of the noise completely? And it is an extra assumption under which it would be trivial. So if I also told you that this epsilon matrix, this noise matrix, is entry-wise uniform in the following sense, it is not only that the fraction of zeros is 1 over p plus epsilon, but actually every entry has probability 1 over p plus epsilon at least to be 0. And also every entry is distributed uniformly over all non-zeros if it is not 0, then now removing the noise is easy. Right, because now I can just take 1 over epsilon squared different R1 and R2s more or less, compute the histogram or just like the plurality in each coordinate, and because the 0 appears more than all of the others, because now all of the others appear with the same probability, that must be lower than 1 over p, because this one is probability higher than 1 over p, then the one I would see the most times, this is the correct one. I'd up to log size of field or something like that for a specific unit. So we could just take many samples and get entry-wise plurality and we would be happy. The question is, why or how can we assume that we have this nicer structure? And the answer is that it is actually quite easy to force this nicer structure. Why is it easy to force this nicer structure? Because the matrices that we are going to query the algorithm with are random or indistinguishable from random. So I can do many things to them without changing their distribution. So for example, I can multiply these matrices with any non-zero random scalar and the distribution would look the same. Right? If I take a random matrix and I multiply it by 2, it's still a random matrix. Good. So for example, if instead of querying the algorithm on A and B, I would query it on Q times A and B for a random non-zero Q, and then I will divide by this Q afterwards, then the second condition I do get, like I get the condition that every non-zero is now distributed uniformly over like every specific entry that is not 0 is now going to be distributed uniformly over all non-zeros. Because I multiplied it with this thing, and the algorithm doesn't know. The algorithm cannot figure out Q because it was a uniform distribution before, it is still uniform distribution. And for the first condition, that it is not just a fraction of indices, but every index is 0 with this and that probability, I can just take random permutations and multiply A and B with them. Permutations are very easy to peel off, of course, right? Because applying a permutation is linear. So I can add the permutation here and add the permutation here and peel them off out of it. So now the query again just looks like 2 random matrices as it looked before, but now I do have these 2 conditions. That the places of the zeros are uniform and the non-zeros are also uniform.
You don't get independence.
No, I get that every entry the plurality will be correct, and I will just take a union bound if I do it like log n times. Yes. Yes, so I just need now to repeat it like log size of field times log n over epsilon squared, and then union bound is enough. So up to logarithmic factors, I am done, and the dependence on epsilon is just quadratic.
Do you really need the random permutations for this to work?
So
I can see you should uniformize the non-zeros.
You maybe can use a little less, but what you're afraid of is something like an algorithm that always in the first entry says 0.
Okay.
Right? Just you want it to
Sure.
yeah, but maybe you can do something that is slightly less.
Okay.
It's quick enough anyway. Good. Both of these examples that I gave, or the 3 examples that I gave, are actually things that we knew or afterwards we know how to do. Maybe besides like the parameters and so on. But we have several other examples for things that we didn't know how to do without these tools. So for example, if I want similar worst case to average case reductions, but not for matrix multiplication, but things like matrix inversion, or solving a linear system, or computing a determinant even, Then this we didn't know how to do with the previous tools, but now we do. All of this now we have the same worst case to average case reductions, again conditioned on these cryptographic things. So for example, if I have an algorithm that computes the determinant of a random matrix slightly better than always answering 0, then I can have, in the same running time, have an algorithm that computes the determinant for any worst case matrix. And as I mentioned in the dimension reduction setting, there is actually a tight connection to a certain type of neural networks in which we now have a faster inference time. So there is like a class of networks in which the first matrix is untrained. The first matrix is essentially just a dimension reduction. So for all of those, we now can have faster inference, faster training in some sense. Good. Another line of work that followed this that I want to mention, starting with actually a concurrent work of Braverman and Newman, but then several works afterwards, was using the same type of construction, the same type of trapdoor matrices, back for the settings of cryptography for the task of trying to do private inference with tools that are actually practical, unlike FHE. Right, so what Mark originally is saying, but then other people afterwards, is that while we could use FHE to say, let a server do some inference for me or do matmuls for me in a way that would not reveal my matrices to the server, this is really impractical. This is efficient only in theory. But using things like this, you can send a matrix to the server that looks random because you added this trapdoor matrix to it, and then you can peel it off by yourself afterwards. So we have a more practical variant of these things currently for matmuls, and then there are follow-ups that are trying to do it for the full inference process. So there are also people from AWS that are actually implementing this, and they have some implementations that they claim are much faster than, I mean, it's very easy to be much faster than FHE, but they're claiming it is getting to be practical. Good. Now I do want to say something about constructions. How would we construct this thing? I will tell you the bottom line first. The bottom line is going to be that it is very easy to construct these things, and we can construct it from nearly any conjecture you would want. And you can think of why, but in the end I will say something about why it should be very easy. But how would we think of constructing this? So the first thing we want to have in mind is that we have many families of matrices for which we have easy multiplication. Say things like low-rank matrices, or things like sparse matrices, very sparse matrices, like only few non-zeros, or things like FFT type matrices, or circular matrices, and so on. So we have all of those families of matrices that we can multiply with quickly. What is the problem? That all of them are very easy to recognize. Right? It's easy to tell if something is low rank, or if something is sparse, or if something is an FFT matrix. So what can we do? Just mix them up. Just let's look at some combination of these simple families, mix it up in a way such that if I know this decomposition, then I can do the multiplication quickly. But if I don't know the decomposition, then decomposing will be hard. So something that we should have in mind as a first step is, yes, matrix rigidity, for example. It should be hard to tell if a matrix is low rank plus sparse. So I'll give you a very simple construction that doesn't get near linear time. It gets to n to the 1.5 time for a matrix vector multiplication.
Does that depend on the parameters as well? LPN assumption?
Yes. Yes. So LPN, it will be based on LPN. I will soon say with which parameters. Yes, but with LPN and some reasonable parameters, I will show an extremely simple way to get n to the 1.5. Which is just going to be to take a random low rank matrix plus a random sparse matrix. Just let's see that the parameters work. And good, let's just say what is LPN. This cryptographic conjecture that I keep mentioning is just saying that if I have noisy linear equations, it should be hard to solve them. So what is LPN? LPN means that I have some secret vector, k-dimensional vector, and now I get samples of the form a random vector and a bit, such that the bit is either a completely uniform random bit, this is like the null case, or the bit is the answer to the linear equation with my secret vector, plus some noise. What do I mean by noise? With some chance I flip this. So the LPN conjecture is that if I pick the right parameter, what are the parameters, the probability of noise and in comparison to the length of the vector, then it should be hard to distinguish if I'm getting linear equations that are noised or completely random answers to each of the linear equations. So this is LPN, and what are the reasonable algorithms or the reasonable conjectures? So essentially the conjecture is that we can't do anything better than collect a set of unnoised linear equations and solve them. Right, so up to lower order factors, what we assume is that we don't have much to do about noised linear equations, again, besides collecting enough linear equations without noise and then doing a Gaussian elimination. So this would mean that it is believed to be hard when essentially the frequency of noise is enough such that in every dimension, the many equations I am getting, I am expecting to see some noise. Right, so as long as p times k, the error rate times the dimension is much larger than 1, then we expect this to be hard. Good. So here is a pictorial way to think of this conjecture. The conjecture is I have my secret vector, I have a lot of linear equations, I have a vector of noise. This is just a vector that is Bernoulli P's. So this is a sparse vector. And I need to distinguish between this and a completely random vector.
Depends to make it vertical.
Not yet, because I want to add things to the drawing. But yeah, we can afterwards discuss the visuals. Yes, and notice that actually in the LPN settings, I'm also giving you this matrix. I'm giving you the equations. But in our construction, I'm not even going to give them to you. So it is only harder in some sense. So LPN means that distinguishing this vector that I'm getting out of this and this vector is hard. And what would we want to do? So what we would essentially want to say is that I want to say that low rank plus sparse is hard to distinguish from a uniform matrix. So essentially what we would want to do is to say if I took many of them independently, so it is not the same S, like with different secrets. If I had like random secrets S1 to say Sn, then this thing, the linear equations time all of those secrets, this is a low rank matrix. This thing, for each of them I got a sparse noise vector. So here I have low rank plus noise. On the other end, I have just a completely random matrix. We want to say that it is hard to distinguish between those two things. What is
rank is because S is reused? Or?
No, so S is not reused.
So what's low rank? K is the rank?
Good, so what is low? Yeah, so the rank is K. So there are n equations and each of them is of size K. This is like n by K times K by n, and this is n by n, and this is n by n. Right, but this is n by n and sparse.
But this like vector of S's is really just a random matrix.
Yeah, so this is really a random matrix, and this is really a random matrix with the correct sparsity. So what is the only problem? Why is this not exactly what LPN says? The problem is that I'm reusing this matrix. So I'm having exactly the same equations in all of those n different ways. So this is the only difference from LPN. But in fact, it doesn't matter that much. So there is a relatively straightforward way to show that, that this is still hard. This is what's usually called a hybrid argument. So what do I mean by that? I mean that if we would look at the sequence of distributions that gets from the uniform distribution to this distribution by just replacing each row at the time to be from random, I will switch it to be this thing, right? Each row here that is random just ends up with giving me a completely random vector. So if all of these rows were actually random and not sparse, then I would have exactly a random matrix that I added to something, so it is uniform anyway. So if I would switch these rows to random one by one, then the entire claim is that if it is hard for every polynomial time algorithm to distinguish the first distribution from the last distribution, then it cannot be that all of these intermediary steps are easy. Right, so good. So what are those intermediary steps? So if I just look at switching one row from random to not random, then this problem, at least, yes, I need to be, if each of them is hard, then the entire thing is hard as well. But what are those intermediary problems? The intermediary problems, these are just LPM. These are exactly LPM. Because what is the problem when I just have one row that could be either random or sparse? This I can reduce to from standard LPM by myself drawing these two random S's, putting two random sparse vectors here, and if I had an algorithm that is faster to distinguish this from a random row here, I would have an algorithm for solving LPM. Because again, I can encode any LPM in this form easily. Good. So this means that these steps cannot be easy, which means that also the distinguishing the first and the last distribution cannot be easy. So what do I get from it? I get from it that as long as for K and P, LPN is hard, then also distinguishing a random rank K matrix plus random sparsity P matrix from a fully uniform matrix is hard. So if I will pick something like K root n, K being root n and P being 1 over root n, so the amount of non-zero entries would be roughly root n in every row, then LPN in the parameter setting, in the parameter range that we mentioned, should be hard, meaning that distinguishing a random matrix of rank root n plus a random matrix of sparsity root n from a uniform matrix should also be hard. And now notice that both matrix of rank root n and matrix of sparsity root n I can multiply with in root n time per row. So this is why this gives me an n to the 1.5 algorithm. Already by just doing the most obvious thing you could think of. And now if you want to get near linear, you don't need to work that much harder, but you need to work slightly harder. So the entire difference would be that instead of just having the sum of two or a few things, we would have some sequence of products and summations, but all with these quite simple creatures. So the decomposition would be slightly more complicated. It is not just a sparse flow plus low rank, it is a product and sum of them, but still if I know the decomposition, each of them is very easy to multiply.
Polynomial of this, and there is a polynomial. Yeah?
It would be actually just like polylogarithmic.
Yeah, no. You sum the product, give you polynomial.
Yes.
The degree will be logarithmic.
Yes, so if you get, degree log n will be enough to get to a near linear time. Good. And as I said, yes.
And you can still use just the LPN assumption.
Yes, you can use just the LPN assumption, or alternatively, you can use other assumptions. So you know how to do it from some other assumptions. In the real matrices, you need slightly different assumptions because you don't know how to connect LPN to real values.
You need also a hybrid argument to argue about this polynomial.
Yes. Yes. But again, I'm trying to argue that it is not hard from whichever conjecture you are starting from. And here is why, morally, what I would want to say. Morally, I would want to say that the reason that it is very easy to construct these families, and we actually know how to do it not only for matrices, but also for random polynomials and random tensors and other things, is because circuit size is hard. In a very strong sense, even in average, even for approximations, even for so on. So what does that mean? This means that morally, nearly for any distribution of functions I can think of, if I will give you either a sample of a function from this distribution or a sample of a function conditioned on having a small circuit, it is very unlikely that you will be able to tell the difference. Right? Why? Because
this is like natural proofs.
Yes, but I mean this is not rigorous in the sense that I would be very happy if there would be like a statement of the form if like some common version of a circuit size approximation is hard for this family, then you can also efficiently construct this trapdoored families for the same distribution. But morally, at least, whenever you have a hardness for circuit size, which is nearly always, you should be able to construct this, and this is why it is not surprising that for many different conjectures you will be able to get it. Because all you want to say is that hiding circuit size is easy. Okay. Let me summarize, so I'm even a bit before time. So the essence of what we are doing is suggesting to wield cryptography not against some malicious adversary, but against the correctness proofs of innocent algorithms. which again is in many senses maybe more believable even. And it is even if it is plausible that some of those conjectures can be broken in some polynomial time, believing that they can be broken faster than matrix multiplication, I don't know, especially by an algorithm that is not trying to do. The other thing is that these trapdoor families should be constructible in many, many different settings. Why? Because whenever estimating circuit size is hard, then it is likely that you can hide the fact that you have a small circuit. And the last thing I want to mention that came up in all of those linear algebraic reductions is that we do know in many settings that there are some barriers for this type of worst case to average case reductions, but all of those barriers are broken if instead of average case, I'm looking at this pseudo-random average case. Right, so what we are doing is essentially not reducing any worst case instance to the same distribution, to say the uniform distribution, but we are reducing every instance to a statistically different distribution that is computationally indistinguishable from, say, the uniform distribution or the same distribution we want to reduce to. And all of the barriers we know of worst case to average case reductions, they fail when you are allowing these type of things.
What barriers can you use?
So like the Trevisan say stuff and things like that. I mean, it's a question of which conjectures would you even make if you want to do it now for NP hard stuff. But I'm just saying that this gives some possible flexibility of not thinking of fully average case, but thinking of something that would fool whatever you are trying to fool to think this is average case without actually statistically mapping every worst case instance to the same distribution. Just gives more flexibility in the reductions. Good. And this is all I wanted to say.
Hey, Nick.
So, or do you have any examples of trapdoors that are not related to matrices? I'm just curious, like what else would the trapdoors be?
I mean, depending on what you call related to matrices. So we can do it for like tensors, related to matrices, yes, for polynomials, but also in a sense you can think of it as related to matrices. So yeah, depending on your definition, but as I said, I suspect you can do it for any distribution of functions that is not super easy for all problems to solve that you want. We just didn't have an example that was useful to us. Yes.
Yeah, it seems like the cryptographic conjectures you need are like much weaker, right? Like the adversary is like an
Yes.
efficient adversary, like with a specific
It's like
timeout.
LPN in sub-cubic time that I hide the
Yeah, the black
equations
box.
from. Yes.
So like, but like this black box form, like, is it possible we could just prove that without proving like some unconditionally strong lower bound?
Very good question. So possibly, I mean, I don't know how to do it, but possibly, because if you, as I mentioned before, if you look at the statement, it is a bit of a ridiculous statement, right? Because you end up saying something like either you can do something about matrix multiplication fast, or you can solve LPN faster than matrix multiplication.
Yeah.
It could be that if you assume that you can solve LPN faster than matrix multiplication, you can also solve matrix multiplication.
Sure.
At this time. So yeah, it could be that, especially for the linear algebraic things that live exactly in the same world as the conjecture, that you can do something in both cases. So we did this.
So another question, like, have you looked at like improving the running times of problems which are really hard, like permanent? Because there's worst case to average case reductions for permanent. Like, could you get some easy form in which the permanent is like maybe not like trivial, but like in, I don't know, improved exponential time or something?
Good. So it's a very good question. We tried to think about it. The problematic thing, or not problematic, but you need to think about it more carefully there, is that if you talk about exponential or super exponential time algorithms, that now the conjecture you are making, you need to make sure that these algorithms are not breaking it anyway, or could not break it.
Like just.
So yes, you need a conjecture that is stronger than the. Yes, so you need to like be able to get an algorithm that is stronger than the conjecture you are making. So either make a stronger conjecture.
But for permanent, if you have a randomness, you can do approximation very well.
Yeah, you can approximate.
But these are all probabilistic algorithms, all of them.
Yeah,
So
yeah. So,
if you allow randomness, then
well, I
the
mean,
question about permanent is
Yeah.
solved. So-
yeah, I mean, we have worst case to average case reductions though for permanent, right? I'm talking about solving permanent exactly.
Exactly, but worst
Yeah.
case over here.
Like in the
okay,
fastest
good,
time you
yeah,
can, like
yeah.
something better than 2 to the n. Yeah.
Yes.
So in this matrix multi worst case to average case reduction, there's this epsilon, and you said there's like a bad dependence in some things and better dependence. So what is the best dependence we have?
Good. So the dependence we are getting, again, assuming cryptographic conjectures, is 1 over epsilon squared. In the like later unconditional works, it is doubly exponential in 1 over epsilon. And there is a very good question of can you unconditionally have a polynomial dependence on epsilon, and also 1 over epsilon squared seems correct, but we didn't think about it enough. Maybe it can be easily shown or not.
I think it was improved to singly exponential and random this year from a difference in like an easier code. Than one that's
Very good.
but still, like there's still a huge.
Good. So now you have 1 log to do it, not 2 logs. Yes.
But still, it's way more complicated than this. So that's a beautiful.
Thanks. Yes. Thank you all again.